Hi, in this video, we want to take a look at hypothesis testing where we've got two samples that we want to take a look at. Now, what we're doing is we're taking the PowerPoint slides from Essential Biostatistics by Bernard Rosner. It's a Cengage textbook. Let's dive in. Let's get to it. All right, so two sample hypothesis testing is where we want to understand if these two different samples have the same parameters in terms of either central tendency or in variance data spread. All right, so for example, if we want to study the relationship between oral contraceptives and the use of and blood pressure in women, and when two different experimental designs may be used to assess this. So in this situation, we've got oral contraceptive women and those who do not use oral contraceptive. And then we want to analyze the blood pressure between the two different groups. We want to see, hey, do they have the same central tendency, the same average blood pressure? Or possibly we want to see, do they have the same or different variance as data spread between the two groups? All right, now a longitudinal study design. We're going to identify a group of non-pregnant premenopausal women of childbearing ages of 16 to 49 who are not currently contraceptive users or oral contraceptive users, and measure their blood pressures. And this will be called the baseline blood pressure. We're going to rescreen the women 1 year later to ascertain a subgroup who have remained non-pregnant throughout the year and have become oral contraceptive users. This is the study population. We're going to then measure the blood pressure of the study population at the follow-up visit. Then compare the baseline and follow-up blood pressures of the women in the study population to determine the difference between blood pressure levels of women when they were using the pill at follow-up and when they weren't using the pill at baseline. All right, and so this is a longitudinal or follow-up study because we've got the same people over time. It's important about how we're going to analyze this is I've got the same person for the data. So when I have the no contraceptive blood pressure and the contraceptive blood pressure, I match them up by the same person. That's an important aspect to the statistical analysis. So because of that, this is called a paired sample design, because each woman is used as her own control on this. Now, a cross-sectional study, we identify both a group of oral contraceptive users and a group of non-oral contraceptive users among non-pregnant premenopausal women of childbearing age and measure their blood pressures. Okay, then we compare the blood pressure levels between the oral contraceptive users and the non-users. All right, so in this cross-sectional study, what we do, we go out, we find a bunch of women who are on contraceptive, we find a bunch that are not, we take our data. Now, we don't have that matching aspect, and so this is why it's cross-sectional. And so we will mathematically handle this differently because I don't have a one-to-one correspondence between the people in each group. In a cross-sectional study, the participants are seen as only one point in time. This study represents an independent sample design because two completely different groups of women are being compared. A cross-sectional study is also less expensive than a follow-up study. Or a paired sample. So the example of the paired sample that we talked about is where we're using the same women for the blood pressure measurements. When each data point in the first sample is matched and related to a unique data point in the second sample. Paired samples may represent two sets of measurements on the same people or on different people who are chosen on an individual basis using matching criteria such as age and sex to be very similar to each other. Independent samples, when the data points in one sample are unrelated to data points in the second sample. For the example under discussion, paired study design is probably more definitive because most influencing factors present at first screening will also be there at the second screening and will not influence the comparison of the blood pressure levels. However, a control group of non-oral contraceptive users would completely rule out possible causes of blood pressure changes. The second type of study can only be considered suggestive because other confounding factors may influence blood pressure and cause an apparent difference to be found when none are actually present. All right, so here we've got this trade-off going on. The paired matching aspect, so where I use the same woman before contraceptive and after contraceptive in the analysis, that is a more definitive, more solid analysis going, but it's harder to execute, it's more expensive, it's more time consuming. The other way to go, where the cross-sectional one, where I just grab all the people I can and then, classify them as contraceptive users, non-contraceptive users, and then do blood pressure. In that situation, it's much cheaper, it's faster, it's easier logistically, but it's not as definitive. So whatever we're doing when we're doing this type of work, we have to evaluate that trade-off. All right, so here we've got 10 women while not using oral contraceptive and while using oral contraceptive later on. And so here we have the blood pressure before they start taking oral contraceptive. Here's the blood pressure after. And here is the difference between the two. The difference is the important part of the analysis for this one. All right, so we're going to assume that the systolic blood pressure of the ith woman is normally distributed at a baseline with mean mu sub I and variance sigma squared. Something that's important to notice is that here we're saying that each person has their own average systolic blood pressure, but we're saying that everybody has the same spread of their blood pressure. And then, so this is at the first evaluation. Here is, we believe that each individual person has their own average. Now, after we follow up, we get the second blood pressure, we're going to assume that everybody's blood pressure has changed by the same amount. Now, each individual woman can have the same personal average at the beginning, and the average here for each individual person is assumed to be the same, plus a constant value being added to all of them. And so the delta is the mean difference in the systolic blood pressure between follow-up and baseline. Now, if delta is equal to 0, the difference is 0. If delta is greater than 0, then we would conclude that the oral contraceptive pill associated with increasing mean systolic blood pressure. If we see that if we conclude that delta is less than 0, then the oral contraceptive pills are associated with lower average blood pressure. All right, so here is our hypothesis testing. So right now, we don't know one direction or the other. We don't know if it would be greater or less. So our goal is just to say, does it make a difference? We're not even going to care if it makes it greater or less than. We just want to know, does it make a difference? No hypothesis is that there's no difference. Alternative is that oral contraceptive creates a difference in blood pressure. And so here is our alternative hypothesis. Now, we're going to assume that mu sub I is unknown, and we're going to take d sub I to be the difference between the two blood pressures. So one thing that's interesting about this is that we're not interested in each individual person's average blood pressure. We are interested in the difference after they start taking contraceptive. And so here is our mean difference, just standard arithmetic average. And so our test statistic will be the average divided by the sample standard deviation of the differences divided by the square root of the number of observations. And so we're going to be doing a t-test on this. And so this is actually just sample standard deviation calculated on the differences. All right, so what we're going to do is if I see that t divided by s divided by the square root of n, if I see that it's far to the left or far to the right in the shaded regions, we will conclude that there is a difference. Now, in this hypothesis testing, we say there is a difference or there is not. We don't specify which direction. So if we see that t test statistic is far to the right or far to the left, we reject the null hypothesis in favor of the alternative. If t is in this wider region of the white, we will fail to reject the null hypothesis. All right, so to compute this, to compute the p-value of the paired t-test, what we do is I take the test statistic, and since I'm going a two-tailed test, I take it here, I take the value of t, and I also take negative times that because we are interested in either direction on this test. So for the p value, what I'm going to do is I am going to slap down the t, slap down negative t, find the shade region outward, and then that will be the p-value of the test. Now to find the cutoffs, what I do is I find the p-value, then that I want overall, I cut it in half, so I'm going the other direction. If I want to figure out the cutoff before I see my data point, what I do is I take the alpha that I want, divide by 2, find the region here that gives me the t, gives me that shade region, take the corresponding alpha divided by 2, find the shade region, find that cutoff, and then that gives me the range of values for to decide what's going on. All right, now in R, the function for this t.test, this is super easy, and it's nice. That gives you the test statistic, it gives you the degrees of freedom, it gives you the p-value, it also gives you the confidence interval, and we get the mean of the differences. Notice that 0 is not inside the confidence interval, so I conclude that there is a difference, a statistically significant difference. All right, so interval estimation for the comparison of means from two paired samples. So here, what we're going to do, we're going to get confidence interval on the difference, not on the actual values themselves. And so then we just do our computation, same way we've been doing it. Take the average, then I subtract the cutoff t that I want, depending on my type 1 error risk tolerance, standard deviation of the difference divided by square root n, and over here I do the same thing, except it's a plus sign instead of a negative sign, and that gives me my confidence interval. Okay, so now what we're going to do, we're going to step into the realm where now I have two different samples. Now I don't have a connecting aspect between them. So in the previous study, I had the same woman before and after she started taking oral contraceptive. Now in this story, in what we're doing now, I'm doing the cross-sectional design, and I don't know, or I don't, there's no connection. There's no way for me to say, hey, these two are equivalent to each other. What I'm going to do, I'm going to say, this is basically a group of people. This is a group of people. I'm going to compute sample statistics. Then I'm going to use the sample statistics from each of these, put them together, and get my test statistic. Okay, so my game plan is when I get the average for each of these, if the difference between the averages is big, then I'm going to, and when I say big, either negative or positive, we will reject the null hypothesis. If it's not big, then I will fail to reject the null. Now, what do I mean by big? Well, we're going to find some cutoffs to figure that out. So whatever the cutoff for that. So what we're going to do, we're going to assume that our two samples are independent. Take the difference of the averages, and we're going to assume that the means are normally distributed. That's not a big assumption by the central limit theorem. And so what we want to do, we want to figure out what is the difference in averages. Well, it works out that if I have independent observations, all my observations are independent of each other, and I have constant variance, then here is the variance of the difference of the averages. And so if I know difference, so if I have this, then I completely know the distribution. It works out that the difference of average of normally distributed random variables is in fact normally distributed, and the variance is just going to be this. So I just take the variance, and I take the the expected value in there, and I know that this difference has to be normally distributed with this mean and this variance. And so all I have to do is just take advantage of that knowledge to work out what's going on. Now, if mu1 is equal to mu2, that is, there's no actual difference, then I know that the mean of the difference is equal to 0. All right, so now if sigma is known, then we can just take this ratio. If I know sigma, I know all this. I know that this has to be standard normally distributed. And so then I just do exactly the same game plan I had previously, where I look up the the p-value, compare it to my type 1 error risk tolerance on the normal curve, or possibly I figure out the cutoffs using the standard normal distribution, then compare my test statistic to the cutoffs. Either way, it'll work out. However, almost every single time, I swear it's going to be this way. You're not going to know the variance. All right, so that previous normal discussion almost never works out. So what we're going to do instead is that we're going to estimate the variance. And here we're going to go with a pooled variance estimate. So what I'm going to do, I'm going to take the sample variance from group 1, sample variance from group 2, and then I'm going to do a weighted average to get the overall pooled variance. So the pooled variance is the variance from the entire group, basically. Then we're going to test this hypothesis that we have no difference in the two populations versus that we do have the difference in the population. Here, this is going to be my test statistic. So notice that this fraction looks a lot like this fraction, except I have an S instead of sigma. All right, that's easy to work with. I'm just taking the sigma, replace it with the S, run through the computations. Now, something that's different now is that since I don't know the variance, I'm estimating it. I no longer have the normal distribution. I have the t distribution. So I'm going to be working with the t distribution. Also, by the way, with modern computers, just don't use the normal distribution for this type of work. Just use the t distribution almost always. All right, so if I see that that t test statistic is far to the left or far to the right, we're going to reject the null hypothesis in favor of the alternative. If it's close to the middle, we're going to fail to reject the null hypothesis. And what we're going to do is we're going to use our knowledge of the distribution and our type 1 error risk tolerance together to figure out what are these cutoffs for what's far to the left and far to the right. All right, so now to compute the p-value of the two-sample t-test, what we're going to do, I'm going to take that test statistic, I'm going to slap it down here, and I'm going to find the shaded region to the left, shaded region to the right, add together. That is my p-value. And then boom, I'm going to put it together, and that will be my my p-value. If that is smaller than my type 1 error risk tolerance, we reject the null hypothesis. If it is greater than my type 1 error risk tolerance, then I will fail to reject the null hypothesis. Now for interval estimation of the difference, so this is going to be confidence interval for the difference. What I'm going to do is I'm going to go through, just like I did before, I'm going to take the difference, then I'm going to subtract the t. This t comes from my type 1 error risk tolerance, alpha, times that estimation, pooled variance, times this funny looking square root. Over here on the right, I do the same thing, but it's a plus sign instead of a minus sign. Okay. If the interval is wide, that indicates that the difference is probably equal to 0. If the interval contains 0, then we fail to reject the null hypothesis. If the interval does not contain 0, we reject the null hypothesis in favor of the alternative. All right, so something that I kind of held back, I didn't tell you the truth, I didn't tell you the full story of it, is that when I do that test that we just looked at, for the pooled variance, we have to double check, do I have constant variance? Does it make sense to say, hey, these two groups have the same variance? So before I can do that, I actually need to run through a hypothesis test first. And on this hypothesis test, I'm going to check to see here, the null hypothesis is that I can use pooled variance. The alternative is if I cannot use pooled variance, then I have to use the technique that we're about to talk to in a little bit. But right now we're only talking about variances. All right, so here, what we want to do, we want to see if these two variances are in fact equal to each other or are they not. All right, so what we're going to do, we're going to take the ratio of the sample variances. So this is a little bit different. A moment ago, when I was dealing with averages, I was using subtraction to check differences. Here, instead, I'm going to use ratios. Why do we use ratios? Because the mathematics of the probability distribution works out very nicely. The concept here is that if this ratio is close to 1, they're the same. That makes sense. Previously, the idea was if the difference of subtraction was close to 0, we conclude that they're the same. For this one, if the ratio, the fraction is close to 1, we conclude that they're the same. All right, so if this ratio is very large or very small, we reject the null hypothesis in favor of the alternative. If this is close to 1, we fail to reject the null hypothesis. All right, so now, the reason why we do this whole ratio business is because mathematically, it works out that we can figure out the distribution. It's called the F distribution. And this was studied by Fisher and Unequal. The variance ratio follows an F distribution when the null hypothesis is that they are equal. Now, something that's kind of important to understand about this is that the F distribution is actually a family of distribution. I have to give two parameters, and that's the degrees of freedom aspect. So the families are indexed by two parameters, the numerator degrees of freedom and the denominator degrees of freedom. And so here, this is how we denote that. All right, the F distribution is generally positive skewed, with the skewness dependent on the relative magnitude of the degrees of freedom. If the numerator degrees of freedom is 1 or 2, then the distribution has a mode at 0. Otherwise, the mode is greater than 0. All right, so what this is saying is that if the numerator degrees of freedom is 1 or 2, then the high point is at the y-axis of the distribution. Otherwise, it's to the right of the y-axis. And so here we can see that the numerator has a degrees of freedom of 1 or 2. Now, here is a mathematical fact, is that because of this relationship here, that if I switch the numerator and the denominator, I can work out the math either way. It doesn't matter for the purpose of the F test. All right, now the F test for the equality of two variances. So what I'm going to do is that I'm going to take the distribution. I'm going to find my cutoffs. So I'm going to look at my type 1 error risk tolerance, cut it in half. I'm going to find the shaded region here. And I'm going to find the shaded region here. So this is alpha over 2 in area. This is alpha over 2 in area. I find this cutoff. I find this cutoff. Notice that this is an asymmetric distribution. If my test statistic lands here or it lands here, I conclude that there's a difference in population variances. If there is a difference in population variances, I cannot use the cross-sectional design that we just talked about. I have to use the one we have not talked about yet. If my test statistic lands in here, we fail to reject the null hypothesis, and I do it exactly the cross-sectional design way we talked about a moment ago. All right, and so here, this is just talking about the relationship between the ratios, or if I switch numerator and denominator. And so here we can see some output. This is from Excel. All right, now unequal variances. So we're in the situation where I want to do that cross-sectional design. I've got two populations of women, one that are taking oral contraceptive, one that is not, and I don't have a connection between them. I ran my hypothesis testing and I concluded that the two groups have different variances. Okay, so now what I need to do is I need to modify how I do my computations. What we're going to do is my test statistic ends up being very similar, but now I have S1 inside the square root on top of N1, S2 inside that square root on top of N2, and then everything is the same. Previously, we had the pooled variance S on the outside of the square root. Instead, we get rid of that and we put S1 squared, S2 squared on the inside. That is going to be my test statistic. So it works out that this difference of averages is normally distributed with this mean, this variance, if the difference between the two population averages is equal to 0, that's normal 0, 1. If I was just by happenstance to know the variances, I would use the normal distribution, but almost surely we don't. So I'm using the t distribution here while estimating the population variances. All right, so the exact distribution of t under the null hypothesis is difficult to derive. There's a couple different ways to figure out what the degrees of freedom are. Honestly, just drop it into the computer, let the machine do it. It's all you'll get pretty close results. If you were doing in Python or R or Excel or SAS, you'll get pretty close to each other. There might be slight differences. Here's how the textbook talks about computing the degrees of freedom. I don't think this is the actual one used in R. It's close, but I think there's a correction term on there. Now, if t is big, is far to the left or far to the right, we reject the null hypothesis and conclude that there is a difference. If the t value is close to 0, we fail to reject the null hypothesis and conclude that there is no statistical difference between the averages. And so here is how to compute the p-value of the test statistic. Take the test statistic, make it negative, and make it positive. Find the area to the right and to the left. All right, so here's our strategy. So first thing I'm going to do when I do a cross-sectional design like this, two independent normally distributed samples, first thing I'm going to do that F test to check to see, do we have constant variance? Not constant, we have equal variances across group. If I have equal variances, I'm going to be using pooled variance on this, assuming equal variances. If I reject the null hypothesis on the F test, then I'm going to perform that T test that we just talked about a moment ago, where we have unequal variances assumed. And so here are some output. So something that is nice about SAS is it spits it out both ways for us. Notice that the degrees of freedom are being estimated when we do not have pooled variance, constant variance. And we get our p-values here. So I would fail to reject the null hypothesis in this case. And computing the confidence interval works out exactly the same. Take the point value estimate, the distribution cutoff, multiply by the standard deviation, and we do a plus or a minus. Boom, we get our confidence interval. Notice that the confidence interval is always centered on the point estimate. That is x1 minus x2, x1 minus x2. And so here is another way to tackle it, or for a different data set using SAS. All right, well, that's all I've got for you for now. Next time I'll tackle outliers. Take care and goodbye.